Hi, my name is Igor Zavalyshyn, and I will present you a Flowverine middleware designed to help building privacy-aware Android applications. This is a joint work with Eduardo Gomes, Nuno Santos, João, Silva, and Axel Legay. So nowadays we have millions of IoT devices on the market, and this talk we will specifically concentrate on wearables, more specifically fitness trackers, smart watches, or even smart glasses. Usually these devices have the following interaction model. There is a device on the left that collects some sensor data, for instance heart rate, and sends it to the companion app that you install on your mobile phone that aggregates this data and displays it to you, and then forwards it to the cloud service, which collects this data, stores it for backup or further processing. The problem of this model, however, is that the device data is stored in the remote cloud service that is outside of reach of the user and the owner of the device, which creates a lot of concerns regarding data privacy from the user side. Like the one as what data is being actually collected by my fitness tracker and why it is being collected in the first place and how it is being used. The same kind of questions can also be raised by the application developers in the situations when their application relies on some third-party SDK to provide a certain service. For instance, targeted advertisement. If the application has advertisement library included in its code, there is a chance that the same sensor data will be collected by the ad code and sent to the corresponding cloud provider. So the application developer can raise a concern such as, can the ad code access user data and send it to Google, for instance? So eventually it all boils down to the question of how do we track sensitive data flows inside the application to ensure data privacy. And it turns out that tracking sensitive data inside Android application is quite a challenging task. Android apps usually have a rather complex structure with a lot of components, with a lot of activities, a lot of components interacting asynchronously, which creates a problem in tracking sensitive data from specific sources to specific things. There are, of course, some static code analysis tools that allow to track such kind of flows, but they're rarely used due to the high false positive rate. There is another problem with implicit data flows, which can be generated by some components writing specific data through the Android API, and another components can read that data afterwards. So such implicit channels for data transfer are really tricky to detect, and although there are some taint tracking tools that allow to find such kind of channels, they usually require changes in the underlying Android operating system, which is not a viable option in most of the cases. And finally, there is no privilege separation across different parts of the same application. So if your application has some third-party SDK included in its code, it will gain the same kind of privileges that the main logic of application has. So that means that, for instance, network to access to network resources will be provided to the ad code as well. And that creates a lot of possibilities for sensitive data leakage, even if the application developer was not intending to do so. And this has been confirmed by numerous cases in use, such as this one, or any others, and mainly due to the inclusion of some third-party SDKs in the application code. Clearly, the Android existing access control mechanism is not sufficient to prevent such data leaks. Hence, we propose Flowverine. Flowverine is a middleware that allows to build Android apps that are private by design. They have explicit data flows inside. They require no changes in the underlying Android operating system, and they make it easier for users and application developers to control the application activity and all the data flows generated in the process. Flowverine middleware provides an API based on element-based programming. It also provides a mechanism for static and dynamic data flows tracking and enforcement of specific information flow control policies. So let's go first through the element-based programming model that is proposed by Flowverine middleware. So with this model, each application component is represented as a graph of elements, and each element represents a functional unit of the application logic. So for instance, here we have an application that collects heart rate data from the fitness tracker and sends it to the Fitbit cloud storage. The application consists of 3 elements. 2 of them are provided as part of the Flowverine API, and they mediate access of the application to the underlying Android API, for instance, to interact with connected devices or with network resources. And there is an element that is provided by the application developer that implements application-specific logic, for instance, processing heart rate data and preparing the payload for HTTP request to the Fitbit server. And Flowverine middleware provides a rich library of such kind of API elements that application developers can use in their applications. Those elements range from those that provide access to various devices and network resources. Others provide UI elements like buttons or text views, and various activity components as well as drivers for multi-threading and inter-process communication. Now, untrusted app elements are run inside sandboxes to prevent them from accessing API elements that were not specifically defined in the application graph. However, they also allow inclusion of various third-party SDKs as part of the application, for instance, add libraries. The problem with that is that those code of third-party SDKs usually was not designed originally to comply with element-based programming model, and thus can contain direct calls to Android API or even to native code. To prevent such kind of behavior of non-modified SDK code, we use dynamic taint tracking techniques. In this case, we provide a tool chain that application developers can use during the application build time. So there is a source code of the application that is compiled to the bytecode, and then using the Flowverine toolchain, we perform so-called weaving using aspect-oriented programming. What it will do is it will scan the bytecode of application looking for patterns that look like calls to the Android API or execution of native code. It will find those patterns and add safety guards to those, which will be triggered during the runtime. Whenever application code will try to execute those flagged calls to Android API, the Flowverine middleware will terminate the application by default. In terms of privacy policies that the users as well as developers of those applications they can specify, it's quite a flexible language that Flowverine provides. For instance, users can specify specific data type that they allow to send to specific data things, in this case to Fitbit, for instance. They can specify that only heart rate data can only be sent there. Developers also can specify specific things that that might not be used to send certain data types. Like in this case, the developer wants to specify that heart rate data may never be sent to the AdWords.com. Now, these policies will be automatically converted to the prologue rules that we use during the verification of the application data flows. And the verification is performed in the following way. We have an application graph that is converted to the application prologue model, which describes all the potential interconnection between the elements inside this given application. Using this prologue model, we create the data flow metric that lists all the discovered data flows inside the given application, listing all the sources of specific data types and all the things that collect those data types. And we have also the policy rules specified by users or developers. And we merge them together to finally define a decision vector, as we call it, which will flag certain data flows to be allowed or blocked depending on the policy rules, and the whole application state, whether it will be allowed to be executed or not, depending on how many flows will be allowed. The runtime of Flowverine looks like this. We have application elements in the top of the image, which communicate between each other through the event bus provided by the Flowverine middleware. On the bottom we have certain drivers that implement the proxy to the Android API. On the left we have security monitor that tracks calls to Android API and also elements that middleware provides. And we have a runtime manager that controls the execution of IFC policies. Now we implemented the various applications to evaluate Flowverine. Here we just list several of them. On the left there is a list of all the applications we developed, and on the right we have a hot body application that displays the UI that the user can see when installing the application. As you can see, it provides information about the certain data type that the application operates with. In this case it's heart rate. It provides the things where this data will be sent to and where this data was collected from, in this case from the connected Mi Band fitness tracker, and it will be sent to a specific URL, and the user is able to block these specific data flows or required to ask every time the application tries to send that data. This is a graph of this specific application, hard body. As you can see at the top of the right side of the image, we have a main app activity graph which collects the heart rate data aggregated across the day and send it to the specific URL. And on the bottom we have ads graph that regulates which advertisement will be displayed in the application. And as you can see, both graphs are not connected. There is no direct data flow from the fitness tracker to the ads graph, which prevents any data leakage. We evaluated the system across different features. We evaluated, first we evaluated developer effort, since Flowverine expects the developers to acquire a new programming model. We evaluated how much effort it requires to switch from one traditional Android development model to the new one. And it turned out that for simple application, indeed you have to write slightly more lines of code, as the case for click counter application, but for the more complex applications that require a lot of access to certain resources, for instance network or devices, we see that Flowverine application require less lines of code. This is mainly due to the fact that application developers can use a lot of existing Flowverine API elements that provide certain features to their application, so they don't need to write those themselves. Now in terms of build time, we have on average 700 milliseconds plus. This is mainly due to the fact that code viewing and to provide the dynamic taint tracking requires some time to process the bytecode and inspect it and find all the calls to direct calls to a native code or Android API and add safety guards. But since the application code has to be built only once, this is acceptable. In terms of runtime performance, we see on average 200 milliseconds overhead when starting application. But later on, all the app activities runtime are comparable. As a conclusion, we presented Flowverine middleware that provides fine-grained information flow control on the Dataflow level. It requires no changes to the underlying Android operating system. It's easy to understand and reason about. It suits the needs of users and application developers, and it's open source. Thank you.